So the next thing that we'll be going over is the energy diagrams for both exothermic and endothermic reactions. So let's just start with exothermic. So this is going to be potential energy, and this is the time. So we start off with a arbitrary amount of reactants in potential energy. There's going to be a rise to reach the activation energy, and then it's going to drop down after that to the products. So the reason that the potential energy goes to kinetic energy is because that exothermic means that heat is released, and that's in the form of kinetic energy. So there's going to be two things that we have to label. First thing is from initial to the maximum point. That's going to be activation energy. And then the difference between the initial and the final is going to be the delta H. So as you can see in a exothermic reaction, the delta H will be negative because the final is a lower value than the initial. Now let's look at the endothermic reaction. So EP, time, seconds, I'll just label the joules here. So here we start with reactants at a low potential energy because they used to be in kinetic energy and you're trying to convert it to potential energy. Go up to the activation energy, comes back down to the products. So here the activation energy will be again from the beginning to the peak, and the delta H is going to be the difference between the final and the initial. So here it's going to be a positive value. As we can see, the final is going to be a greater magnitude than the low initial. Another thing that we have to note is that, not specifically relating to the diagrams, but it's an important thing that we should know that. So in a closed system, H, so closed, H is going to be always formed in a liquid. So that's water vapor or liquid water. Sorry about that. And in an open system, H2O is going to be a gas. Okay, so I'm not actually sure what I was. Oh wait, yeah. So another notation for enthalpy is if it's like this. So enthalpy with a subscript R, that means it's the enthalpy of. Let's just type this out. So it's the enthalpy of a reaction, and if we have the delta and like CH, that's just going to be enthalpy of formation. And like, oh sorry, I got ahead of myself. So that would be combustion, and then F would be formation. Yeah. So another thing that we can add to this is this O kind of symbol in the superscript. What this suggests is that the enthalpy at SATP conditions or standard conditions. Open system. So that means stuff can escape in open. And in an isolated system or closed system, that means products are contained. Example on calorimetry. So yeah, that just brings us to our next point. What is calorimetry? So calorimetry is where we can experimentally determine like specific specific heat capacities or all kinds of information based off of a reaction. How it usually happens is that uh, we have like a calorimetry cup. The most efficient ones are usually polystyrene or styrene because it's usually heat doesn't get transferred to it, so like it's pretty efficient. It's gonna be full of like a substance such as water. We're gonna have like a metal, or we're also gonna have like a temperature probe, just a simple temperature thermometer. We're gonna put that into here. We're gonna record the initial temperatures of each first of all, and then we're gonna record the temperature at equilibrium, which is like the final temperature that the two substances mix together to form. So how do you do a calculation regarding calorimetry? Let's just type this out so it would be neater. So Q, heat gained by water, is equal to the opposite of Q lost by the metal or whatever we're using. So that just means that all of the heat that we put into the water, or all of the heat that gets gained by the water, is all of the heat that got lost by the metal. So that's for a styrene calorimeter, which means that it is like so efficient that heat loss from the calorimeter is basically negligible. But that's not always the case. So if that's not the case, like if we use like a metal calorimeter because like for example we were doing like a combustion and we don't want to burn something in styrofoam because it's not going to be good, we're going to have to do Q lost by the metal plus the Q that is absorbed by the calorimeter. Oh, sorry, that was actually supposed to be on the other side. Heat absorbed gained by calorimeter. Okay, that's out of the frame now. So yeah, the heat gained by the water plus the heat that's gained by the calorimeter. Just fix the parenthesis. So those are the two gains, and the loss is all from the metal because the metal is going to be at a higher initial temperature in this case. Hess's law. So Hess's law is like a method of predicting the enthalpies of reaction. So like if we were gonna write that out, predicting enthalpy of reaction. So there's two main ways that we can do this. The first way, let's just write it out quickly or type it out so that it looks better. So we have, for example, C2H5OH, which is what was it? Ethanol. It combusts O2. This is the gas. This is the liquid. Let's just make the font a bit smaller. Goes to 2CO2 gas plus 3H2O gas. Crap. So right, that's the reaction. If the question is like this, it will also give us a question, the other reactions. So decomposition of the ethanol. So that has a 277.6 kilojoule delta H. Right, so then we have another reaction, just the formation of the carbon dioxide. Correct. Oh yeah, and that one's gonna be a negative 393.5 molar enthalpy of, and the third reaction that they would give us is 1/2 is the formation of water or gaseous water, water vapor. Let's just add moles to these. Feel free to like skip ahead a bit in this video so that you don't have to just watch me typing out these reactions. Should have had them out like before making the video, but it is what it is. Okay, so the first method of doing this is by balancing these three reactions so that they can form the net reaction. So let's see that we have 3 oxygen on the reactant side. So here there's going to be half a oxygen on the product side in the first reaction. There's going to be a singular oxygen, and there's going to be a half oxygen. So let's look at something else first. So carbon dioxide, there's going to be 2. We see that there's 1 in the second reaction, so that means we could just multiply that by 2, this whole reaction, including the enthalpy, molar enthalpy. Then we look at water. That's going to be the third reaction, 3H2O. Multiply everything. Oh wait, I forgot to write the negative 241.8. So yeah, and then let's see, 3 times 1/2 is 1.5 oxygen plus 2 equals 3.5 oxygen. There's half oxygen on this side, so that 0.5 cancels out to bring you 3 oxygen. So that means we balance this correctly. And how we then do it is that we sum up the enthalpies of the product side. So 3 times negative 241, or actually, yeah, reacted minus product, I mean, sorry. So let's see this. Just type it out. Prediction of reactant enthalpy is equal to the reactant to 277 plus 2 times negative 3.93, which is negative 7.25, 7.87 I mean, and then 3 times negative 21, that's going to be negative 7.25, or just 725. That's equal to negative 1234.8. So this is the long way of doing this question. There is a simpler way of doing this question which doesn't require as much steps or even these 3 reactions. So we're going to do that next. Let's just erase these because we don't need it for this method. So this method, it just uses this mathematical formula. So sum of the enthalpies of the products minus the sum of the enthalpies of the formation enthalpies of the reactants. So products 2CO2, 3H2O gas. We would go back to this table and look for those. So H2O, CO2. Yeah, here. Negative 3.93.5 kilojoules per mole. H2O gas is going to be down here. Let's go back to that question. And then product C2H5OH ethanol. Let's look for that. This is in alphabetical order, so it's easier to look for stuff. Yeah, here. Alright, so equals products 2 times the carbon one, which was, let's just go back again, 393.5, and the water is negative 241. This should be negative as well. And then that minus the reactants. Oxygen gas doesn't have a enthalpy because yeah, negative 277.6. That's just one mole, but the negatives cancel out, so that would just be a plus. And the answer that you get out of this should be the same answer as we got previously, which is negative 1234.8 kilojoules and that's per mole. Okay, collision theory is that this theory where it says that for a chemical reaction to occur, a collision has to be effective. So what does that mean? First of all, it means that they have to have the correct orientation. So like, if we have like two, so if these go on head on, it would not be effective because it's the same thing like hitting itself. If we have something like this, and then these hit, then it is effective because they're different particles and they're reacted together. So that's what it means by orientation. Enough collision activation energy just means like enough collision activation energy to reach that peak and complete the reaction as we saw in the exothermic and endothermic energy graphs. So that's also called like threshold energy. Right, so activation energy for a reverse reaction is a formula that we must know. So activation energy reverse is equal to the activation energy of the forward reaction minus the enthalpy of reaction. So we should have the sign of the enthalpy, so if it was negative or plus, so like if it was exothermic, then it would be a negative, and then forward plus that would be a positive value, which means the enthalpy of reverse is going to be endothermic. Catalysts are going to be the final thing that we have to worry about in this unit. So a catalyst takes part in a reaction, and however, it doesn't get consumed in the net reaction. So it just increases the rate of reaction. And how you can see it is like, for example, analogy, we have like a bike, right? So say that's a bike, it's racing up a hill. Everyone that's on that bike has to, like everyone's on this bike, it has to go up that exact same hill. However, if we increase like different pathways, like pathways on the right side of the mountain, pathways zig and zag up the mountain, then that just means there's more pathways for the bikes to go up, which means the time it takes to proceed the reaction is going to occur at a faster rate. So if we can look at this in like a biological system, this kind of relates to biology 20. In biological enzymes, which are like the catalysts in the biological system, it's like a substrate with like a lock and key kind of fit, except not necessarily, but you can think of it this way. So the substrates are the ones that go into the enzyme, which is the catalyst. So the substrates have to be the exact shape to fit into the enzyme to have the reaction work, and then like for example this enzyme binds these two together, like goes into it, and then it comes out being one. So yeah, that's all there is to the thermochemistry unit of the chemistry 30 curriculum. I hope that this video was informative and taught you a bit about this unit and help make some of the concepts easier to grasp. If you have any constructive criticism, please let me know in the comments, and also if you have any video suggestions, please let me know as well. Thank you for watching.